Good evening, gentle readers. It's August the 19th, 2024, Monday evening. About 6:23. So what I hope to do today would be to continue on with Moment in Motion. Moment in Motion, a dialogue or a monologue about the dialogue of what it is that is a theory that helps to express, to relay, that there is a formalism of a mathematical fact that is the theory of the quantification of elements in relative motion to each other and the moments as when those motions are dynamic, and make as of the dunamis and the dynamis, which is discussed long ago here, as of the potentials, which are the real fields, contrive to comprise change. And that in such a manner, this very well explored field of the mechanics of motion has been studied here over quite a few readings of the literature, ranging over the classical to the pre-classical and even prehistorical studies, through the medieval, into the Enlightenment age, through the age of modern technology and into today, and into the premier theories of today, general relativity and quantum mechanics, which is explained as being a continuum mechanics, and that there's a fall gravity in the middle of that, and then the general relativity is with space frames and frame spaces, implementing for space contraction a neo-Lorentzian sort of Einsteinian in the limit, or actually falling out of the limit, theory of relativity also. That for then this 0 meters per second being infinity seconds per meter, that the zeroth laws of motion still add up to something more than no opinion, period. Opinion, no opinion. So why we've gotten here to that 0 meters per second is infinity seconds per meter, and that this is from that as acceleration has to take into account not just a higher order of acceleration that changes it, and not just a higher order of acceleration that changes it, not just that force is a continuous function of time, ranging, for example, between 0 and 1 and having at some point each value in between, that there are no jumps, that continuity is everywhere, there are no discontinuities. That not only must account for these infinitely many higher orders of acceleration, and meters per second and seconds per meter, and meters per second per second per second, seconds per meter per meter per meter. And each one of the combinations of the dimensions, these two, and then for mostly with regards to our 3 dimensions of space-time and 1/2 dimension or array of time, that these are the things we get to and arrive at here, and are kind of well explored and being considered in his course with how to make it so that this dimensional resonator and dimensional alternator that indicate instead of the usual picture where you draw some coordinate setting and have the object as its motion described as by the setting, that everywhere objects are just kind of independent, unique, and have their own coordinate space. They got to have their own frames, as it were, and then to figure out how that adds up for then the orbits to be all around them, instead of just simply centrally the other way around, which is great when you have one map and everything fits on it. But when you instead have that there are independent objects at all, this gets into the very ideas of these inversions that fill out the complement of things that make for that our geodesy, all our world lines of our theory of this mechanics, which you can call relativity or general relativity if you're so interested and know what you're talking about, that this is the kind of way it then is contrived to be this way in the same thing, while yet being a very, very much so that it's that each object is its own origin in this way. Now, of course, mathematics is very, very well explored, and there's not much reason to expect that anything new under the sun will ever arrive from some simple kind of knockabout or turning over the field such as this. Indeed, one would expect that it would be the duty of the diligence, any kind of academic person who is studying it, a researcher, before they went out of field making any kinds of theories of their own, that they went around looking through all the historical theories, so they knew all the sorts of different experiments which went into arriving at these things, instead of just saying that, for example, well, I'm just going to go count frogs and then estimate from how long they leap, that when I learned the theory of how they learned that electrical current stimulates muscles or something like that, that I could apply that directly. It's relevant to go looking for these things, vis-a-vis that, of course, you're fully and freely and welcome as you possibly could be to make of yourself your own entire theory and all your own formalism and whatever style you may so carry. In what results a universal language of mathematics that would be equally interpretably, equally interpretable, equi-interpretably, the same things. And indeed, there's no reason at all to resort to demonstrating that the canon builds to this thing all the way along the story of the historiography of mathematics as a science, and mathematics as a philosophy, and mathematics as a belief system for the humanity's brief historical record on Earth, fellow Earthlings. That today is just kind of reflecting on that. It's a pretty great field, and you can start anywhere in it, and it can always make sense. And that first of all the most simple and obvious and clear things are always a given, and that's why we call that classical. And that's why something like Galileo's laws and Newton's laws and those being kind of like all the laws that are called classical and in effect, because they are just always so simple. Motion, rest, equal opposite, defining force as mass times acceleration as at an instant, just saying that it exists, besides, because otherwise you could apply the same thing as like, well, changes in velocity don't exist. But they go to the second order for acceleration, this is so far what we've arrived at till we get to the fictitious and this kind of thing. But then above that, it's just a matter of analysis and finite element analysis and finite steps of the step size, the evolution of the carriage of the thing, vis-a-vis the analysis of otherwise the linear and the continuous terms, and all such manners of any kind of shape or anything that makes a jig or anything that makes records of a way to construct any of these paths or their products that are these quantities after inertia, which is like dead weight, it's inertia, and it's what so carries, and then momentum, which is like this carrying weight, and then also it's considered the conserved quantity because it's right up in that second order, whereas all the other stuff like the Laplacians fall off again this other way. That what it is it has that momentum is considered then the pseudo-momentum. And there's a great paper about 30 years ago or 40 years ago, and it's like pseudo-momentum does not exist. And so it doesn't. It's fictitious in this sense. And then why it is that that's still so relevant to these systems of equations like the centripetal or the centrifugal has that it really is the centrifugal that's real. That the centripetal is as to it in the development of the form of the equation of the function of the formulas of motion as about the rotational. That is the real part, the centrifugal, the true centrifugal. So this just again helps to affect to reflect that the dynamics of the definition are what keep things going on, and it has to be accounted for. And so this kind of deconstructive account is bringing for that. Then when these things come back together and they're more holistic as of sorts. A reconstruction of the things. This is as what results that the theory is embittered because where it's at is bereft of what is an entire necessary contingent argument, a development that sustains it throughout the entire necessity of what it must convey, that 0 meters per second is infinity seconds per minute. And any change of that at all is all the way down from infinity. It's similar as with regards to relativity and Einstein. It's like, Einstein, what's your theory of relativity? It's like, in my theory of relativity, gravity is down. So that's great, Einstein. So you're telling me that gravity always points one direction in relativity, and it's down. He's like, yeah, straight down. And so in this manner, he's just arrived at that's the rule. But anything about the whole centrally symmetric and things arriving back in terms of the rotational at all makes up the entire rest of his career in the total field theory, to where you arrive at this centrally symmetric Einstein's bridge, Einstein's second most famous mass energy formula that nobody's ever heard of at all. So these very notions of the classical and the linear, and how superclassically and paleo-classically, because very much so the ancient thinkers come up with these same things. Very much so, because they had even less to fill it in the middle, and towards the 25 orders of decimal magnitude of big science's data. They had entirely the classical and the superclassical as of just turning things over in their mind. So the superclassical, as of that all the real fields are the fields of potential, this dunamis, the dynamis, for the energia being the fungible and what's in the middle, the measurable close up, that everything else adds up about as around it. So that's just kind of a justification to help explain why, in the very well explored and turnover parts of this field, it's necessary to have a pretty deft understanding of how things work, and particularly at least the two-dimensional and three-dimensional mechanics. Because it arrives at that without knowing that, then it's just as bad that you can't really develop the mechanics of otherwise at rest a roller coaster, or something as along the lines of this ski jump is given, or molecular mechanics, before getting into other fields besides the kinetic and the kinematic. That all these kinds of things to do with even being able to justify the usual sort of navigating and getting around and surviving in traffic and all this kind of stuff. That there's a first part, and it's necessary, and it's to know all this classical milieu. That then as we arrive at this higher level necessity, and that the effects of the pseudo-momentum start to take effect in the rotational, in the classical, and it's not just fictitious forces, and it's not just always advantage, or something along the lines of the G forces aren't real. And we even get into this discussions here about whether the equivalence principle is only terrestrial, because it is, and that it's shown there's frame dragging and stuff like that in the big science of the day, where something like James Webb telescope and after two mass about 20 or 30 years ago totally opened the eyes of big science and astronomy, that the celestial sky survey had been entirely halfway capable of estimating its own sphere of influence and effect. So I find this pretty fun and compelling. Because first, what I really enjoy about mathematics is continuity and trying to understand the discrete and continuous, or the digital and the analog. And this is the traditional names when they were inventing the solid state in mechanics of the electronics and electronic circuits, vis-a-vis the electrical and electrical circuits. There was arrived at this notion of after something like the vacuum tube, where the field effect device was implemented in the anode and cathode according to a grating to make for power amplifiers and the op amp and all these many configurations of what's called the vacuum tube for the electrical devices and the passive and current driven devices. That then, as we reached further into the realm of the silicon transistor and the transistor network and the solid state electronics, the solid state power electronics and this kind of thing, that it came to arrive at that the analog and the digital started really making a big difference, because what was opened up was this entire world of the digital, where this very most simplest thing called a cascading array of NAND gates, in terms of like some a field gate of gate arrays, made it so that it's possible then, as fast as a clock chip could drive that, then the output trace could drive a result off that. That it became systolic and clock driven as fast as, according to the electrical circuitry, that a clock could drive this systolic solid state transistor network of a chip, that it would be able to compute digital results. Now, before that, everything was done with an analog computer. And it's still to this day possible, for example, as we look at something like Morgan's electromechanical effects and applications, about how it's implemented something like the D-Wave quantum simulating computer, that the idea of the analog computer led to many things that far, far outweigh in this real time, this systolic nature, otherwise the very general purpose of the digital. So in studying the mathematics about the digital and the analog, it's much as of the matters of the continuous and discrete. And so you can take of that, on the one hand, the is whether the whole is the discrete, or only the discontinuous is the discrete. For example, apples and oranges, whether it's out of the entire universe just a whole where an apple lives, or if it's just an apple in the entire universe. So it's in the universals and particulars too. Logically, one arrives at all these things from thinking about the discrete and the finite and the digital and the continuous and the infinite and the analog. These then affecting to relay, that in the course of trying to formalize these things, that what's arrived at is a lot of these same things that get into these paradoxes they're called of Zeno, or paradoxes they're called of motion, that somehow don't exist. So the fact that motion occurs at all, and you can find any given scientific experiment very quickly dispel any notion that it doesn't, according to anything that has observer and the observational sampling and the measurement effects available for a theory with falsifiability and reproducibility, that what goes up must come down has always been in effect, in terms of continuous motion, then it must be so that all this kind of stuff is so. A lot of this came up in the study of like atomism and stuff, in terms of wanting to know how to use mathematics, figuring that, okay, mathematics is a universal language. Mathematics is a universal language, and there's nothing that it can't do. There's nothing that cannot be expressed as an object of mathematics, in the language of mathematics, in the universe of mathematical objects. There's nothing that it can't do. So we're human beings. Obviously, there's a ton of stuff we can't do. All we can really do is reach to our limits, and from those, we hope to use these incredibly powerful levers of mathematics to make it so that then, as with regards to anything that mathematics can do, it can do for you. So this is the idea of then trying to grow and learn as a thinking being, beyond being just kind of like an eating being a thinking being, where what becomes a sustenance is the idea, and this kind of thing, vis-a-vis that sustenance is love, or whatever it may well be. That the idea of becoming competent in mathematics then takes a great long course. So one figures that it helps to know at least two things. One, how the classical and linear and instructional and the curricular is laid out for everybody around the world, because then figuring at least that would be well understood by everybody. And the other is like how this foundations comes up that is considered by as well as can be understood at the time, how the entire theory arises and from what and to where. This is the foundations bit. And then finally, the second greater foundations is like into what, until we don't need any more laws. In fact, there isn't much left after we figured out 0 meters per second and infinity seconds per meter, that the rest is just kind of detail. But right now we're looking at these vague and wavy laws of large numbers, because there are more than one. And so whether it's something about the analog or digital or continuous or discrete, or otherwise that it's about the dynamics of the things with regards to these various things having to do with the continuum mechanics, is for mathematics, for a theory to arrive at, for there to be one at all, for there to be a language to be able to consider this by the human means of communication. And the fact that everybody's basically limited to the same toolkit of one brain and one mouth and one pair of ears and the eyes and the other senses, of course. But just that there's communication and conception, and then anything else is just a matter of subjective, objective distinction. These kinds of things. So it's pretty thorough to try to address a personal approach towards the foundations of mathematics, when the only way that one can really arrive at such a thing is to make the journey mostly themselves. To have come up as be able to say that they have facility and they've exercised it. And then to be able to come up and come through the canon and the gauntlet of sorts of trying to figure out what is, everything that's necessarily true of the entire theory, foundations, and then foundations again. This can be assisted with some, instruction and exposure by all means. But it takes much to cultivate it, and it takes mostly personal dedication and the luxury of a lot of time. And also of a particular socioeconomic background that makes it possible to carry such out. Thusly, anybody can learn as much mathematics as there is. Over time. So where we arrived at is something like this. In the last discussion, what there was a reading from Kodaira, who's an algebraic geometer. And what he does is he arrives at a lot of the development that's gone into the making analysis tractable, and for the tensorial products, these coordinate settings, and making it possible to compute where things are generally. Making means for this sensibility, fungibility, and then this tractability, that mathematics can do anything, and we can make mathematics do anything. And so it's just kind of a matter of making that so it is sensible, and then figuring out how it's fungible, making that tractable. Because eventually it's upon us, or the applicant, the applicator, to make it so that it's tractable and is tracted, widely. That this kind of development was picked up by Kodaira as taking the kind of one of these similar deconstructive accounts of the entire Gaussian Eulerian complex diagram after de Moivre, built off of trigonometry's identity, off of the inverse powers of the roots of unity, and this kind of thing, back into a space of vector bundles, and then building that back up and out, and showing how it made back and forth together between them. Completions. So this continuity is the whole idea of Zeno of Lea's these aren't the paradoxes of motion people have been telling you about. This is that both ways, it's got to be solved both ways, either way. So one of these completions is this geometric series called the inverse powers of 2. They sum up to exactly equal 1. It's the only way to do it. Everything else has got to be contrived on its own way, but this is as a leg of the scaffold will stand up by itself. This kind of thing. Kodaira shows an example of taking a deconstructive account, which was being built up as the greatest edifice, and nobody could climb back down from it because the handles, the knobs, the dials were way up there on top of it. So all the linear analysis and the bigger theory, and also resultingly this stuff about the quantum mechanics, for example, could all be readdressed in this manner. And then there was some reading from Zariski as another example of an algebraic geometer who got some lots of these different differential forms, and help us explain and illustrate that, yeah, there's lots of different ways to rewrite a given part of these things about the equity-interpretability of it, equi-interpretability, and to help it so arrive at that what's so is so again. So what I hope today to do was just kind of pick up as on that course. And so I'm reminded as of reading from the beginning of the Moments in Motion, this series. And a lot what it was deemed to be about was the waves. So the mechanics of waves basically makes for so that in the mechanics of waves that it's a model of change in an open system, because the amplitude of a wave is infinitely variable. And so the amplitude of a wave can have all the character of anything to do with the real number. And as well, the amplitude of a wave can be an infinitesimal, or in a sense then related to other waves of whole magnitudes, infinite. And so in this sense, what it makes for as otherwise of a real number is a reflection on changes over spaces of real numbers, or as the extended domain in real numbers. Then there is that waves are particularly associated with periodic motion, that is a motion of given time, this universal parameter, all the effectively constant revolutions in time of periodic oscillating motion, constant motion, that it began as that the wave was the milieu of things. Now this is not quite the same as starting to saying, well, like it's lines, or it's atoms, or it's a spiral that might start everything. These are some other ideas of whatever else there could be of these extended regions of otherwise just numbers, two quantities, two magnitudes, alike different, according to the isoparametric theorem in all forms, according to all the relations of means in all forms, according to all relations of geometry. Geometry is motion, perspective and projective, all these kinds of things. Mathematics is relation. So trying to figure out a very fungible form of this for waves is that it's also already totally well arrived at already. Because this gets into, after trying to learn about the continuous and the discrete and learn in mathematics that can do continuous things, it's called calculus. And everybody started to learn that in school, and or at least when I was hoping to get enough education to be able to get a science degree. So what we got to study in was calculus. That was the course. That's what was offered. That's what everybody could sit. That's what everybody got, the same instruction, the same exercises, the same presentation of all the theorems, and the ability to walk out of the class and having said that they sat the same class as everybody else across the entire country in that class. And they got the same education. And they knew the same things. And so it was, in this sense, true for all of them, all the mathematical facts so associated. So after that, the most enriching thing in terms of mathematics as a model of thing for the world of physics was not just the classical mechanics and motion that was begun to be introduced, and not just the notions of the electrical and the magnetic, which was also begun to be introduced, but the particle wave duality. The particle wave duality, besides something like the stoichiometric chemistry, which was presented as pretty much entirely and terrifically, meaning in this sense, wonderfully, is according to ratio, stoichiometrically. The particle wave duality establishes the very first sort of superclassical concept to this correct sort of curriculum. And so the particle wave duality it makes it so that as a concept, it intends to convey the entire kernel of the development of the concept that is dynamic in form while at the same time well-defined and well-formed. So waves was considered as that then the waves can be considered to just fall apart or take where they coalesce and make particle theories, or they can consider where they build it up higher and make theories of other waves, or they use extended regions of those and make resonances. That this is also how it is today in terms of how theory calls these things, that to be equity-interpretable, first use the same names that there are and don't get them wrong. That there is a very, very high bar of the standard of usage of terms, and it's expected that they're always correct and not sloppy at all. That for these particles and waves, then learning it and expanding and expounding upon it this way keeps things simpatico and copacetic and at the same time compatible with all these other further developments in the field. This oscillating and recitative, this attenuative and dissipating, the tendencies and propensities, a theory of some histories, of a theory of some potentials, is what's arrived at here for least action and a gradient. So that's been going pretty well, or at least in the sense that as far as physics theories has gone, I have designed this sort of my approach to it because this is largely what I've pulled together from all my influences and teachings and instructions and theorems and readings and random occurrences or whatever just the birds might chirp or any other kinds of influences. My theory is entirely indisputable in these kinds of senses. As I've had the chance and plenty of time, I was like, well, it's kind of like making up an ideal kind of thing, and it's only for its own sake. So you got no attachments. There's no ontological commitment to make except for that which you find meets these true utter pragma of the scientific theory for mathematical theory. Theory of logic is what makes for your scientific theory. It's a theory of physics, and it supports statistical inference. So in this sense, this theory of sum of histories, theory of sum of potentials, is entirely strong as mathematical theory. When we're looking for a theory of everything, there's nothing else it could be. So that just helps to just establish a little bit more thoroughly that that's what it is. And then, for example, with it, it's like, well, what happens in such a theory? It's like, well, there's oscillation and restitution and attenuation and dissipation. And if either of those isn't quite accurate to reflect what it is that's going on, then a couple of them do. And among the four of them, they kind of build this idea of the square of opposition, the dialectic, and the meeting in the middle of nowhere. The deductive impasse for deductive carriage both ways, of the inductive impasse and all this kind of thing. So for inference, for logic and reason, is to follow that these are the properties that can be used for description of these things. Thus, when attached to the language of these things, it will eventually so ultimately apply that it will be equi-interpretable with any other possible putative correct theory of everything physical and mathematical at all. So, inspired by quantum mechanics and relativity and a thorough study of their background developments and concepts, their conflicts, and as well what their strengths are and why otherwise fruitful avenues may have been abandoned, and then carrying that forward into all the big data, big sciences, big data, since 100 or so years ago. And before then, there was essentially fundamentally so related nil data, except for that the sky survey was always around, and there were some big sundials, basically. What we've arrived at today is so much data that is a theory that it can start explaining all this stuff at once. It can gain a lot of ground just automatically by explaining some facts and convergence and continuum mechanics as of about laws of large numbers, which may be so arrived at in simple means. Now that's getting pretty grandiose, because it's expected to have come up with a bunch of different theorems about laws of large numbers. And so here I only have a couple different non-standard theorems affecting to reflect discoveries in laws of large numbers. Real analytical character, otherwise unavailable to inductive inference, found via deductive inference. Courtesy property is basically of a theory with foundations that's coming up from not much at all, a null axiom theory, an axiomless geometry, providing all of like Euclid's geometry, which is very familiar to everybody, providing of course 3 different continuous domains, providing of course all the objects familiar as something like Zermelo-Fraenkel set theory, with or without the axiom of choice. Take it or leave it, your pick, It's just a fragment. And carrying along with these kinds of things. Standard. And then this extraordinary or super standard is where the real possibilities lay in not just changing the language as of about old things, old wrapped as new, but figuring out actually something kind of new in the language that we already have. There already is a full language of mathematics. It needs attention. The Hilbert's Infinite Living Museum of Mathematics is open for everybody, and most of it is woefully undervisited. But there are still to this day many nice little nooks, and somebody's always working on them, or somebody very carefully swept it out 150 years ago and left a little light on there, ready to be found deep in the stacks of all the mathematical journals over time. There's enough developments still that there's many features of this kind of theory. Then a lot of them are equity interpretable again. So trying to figure out how to kind of make for a catalog of that, and also for like when they build in from the smaller theorems, like from just a few circles or trigonometry or some of these other kinds of things, and where they can fall apart back together again, like the parabola and the quadratic sieve, marking on a line all the prime numbers and not the composite ones, the quadratic prime sieve. Or for something like trigonometry, how about trilateralometry? It's kind of like trigonometry, but you can take an equilateral triangle instead of a right triangle and just unhinge it, and it draws the same functions. All these kinds of things. That moment of motion I've really enjoyed. I've enjoyed kind of getting into this, because then I've been able to cover like a lot of different particularly important seeming subfields, and relating all kinds of things from like the fundamentals of science and the physical theory to applications that to this day I still see a lot of research going on, and that a lot of their application was figured out like in the 1970s and 1980s and written out as a Fortran program. And every 5 years they've rewritten this Fortran program as like a numerical finite element analysis for a bigger box. And then about maybe about 20 years after that, they rewrote it to kind of like to have a slightly different model of computing or something like that. The same algorithm, vis-a-vis the symbolic solver and stuff like that. That's where I see that a lot of the possibilities is kind of in the middle of that somewhere. That there's a sweet spot somewhere between where the primary inventors of good mathematics and big science in the 1970s, 1960s, 70s, and 80s left off, then handing that off to numerical methods and solvers, and so they started to deliver just these greatest benefits of all these things. And that since then, it's just been people just pick that up and say, great, problem solved, vis-a-vis what other developments there could be. And then it's hard to figure out sometimes when you see something in the lab, it's like, well, we just got a bigger computer. Well, we just got some finer bits, some finer dust here or something like that. It's hard to find sometimes, whereas actually is like Fritz London providing the formulas of superfluidity, entirely changing how things are considered. Bowman de Broglie, compared to the at odds either ways of it's Fresnel, well, it's Newton, it's photons, it's waves. It's like it's super classical. It deserves more than what it's got, because all we're looking at is kind of a weak after image of it. That's what it seems like sometimes. So with the remarkable development of this, which has been declared as a new sort of units of computing, an embarrassment of riches of computing resources, that a given coffee break can result like 5 million. Oh, what's the word? I'm not quite sure what it makes. Biz kits or something like that, I suppose. An embarrassment of computing resources, that there's been very little to no incentive to improve the analytical basis for things. So how to do that when the publisher perish generally would drive people to not really add value, to add perceived value. Here then, it's just generally considered a usual sort of course. Well, you got to start from the beginning. And so with the idea then that there can be one theory at all, it's kind of sort of established that here's the desiderata, what's desired, and the requirements at all of what such a thing at all must be. Es muss sein. So in this manner, I've at least set myself up to be able to explain, to relate to somebody is like, whatever you're going to possibly say is the theory of everything, physics-wise, science-wise, mathematics-wise, because it has to offer for mathematical science and mathematical physics all of what mathematics is. It's got to satisfy all this. And then for physics, it's sort of a ride to the similar kind of thing. It's like, well, I already kind of have all the theory of relativity and quantum mechanics sitting here, and a bunch of this stuff underneath it called continuum mechanics and space contraction. I won't accept anything else than that, that this is kind of useful, I think. How about the theory of gravity? Well, we've got one where it doesn't involve a violation of all our principles of the conservation of energy. It's fall gravity. That's great. That's what it is. Now, coming up with the formulas, of course, is the only reason they get prizes. It does not matter if it's qualitative. It does not matter if it's correct in such a manner. It does not matter if there's nothing wrong with it at all except just having to come up with the numbers. Without the numbers, it is not worth bubkus or squat, as they say sometimes. It is not worth any type of credit towards a prize without having the quantification of these things. So, like I said, it's very critical to have it all line up with this classical theory and all of classical theory and relativity and quantum mechanics and all these things that add up. They give all the perfect numbers for all this stuff. 0 meters per second, infinity is seconds per meter. Now we bring that in too. Now it's got to add up with that too. These are the kinds of things. So yeah, I've enjoyed this today. This is just kind of discussion about nothing, in the usual sense of everything that a theory must be. And the ability to make the idea being, again, as an ontological sort of commitment, as a reliance on something, or that you bind yourself to something, that you voluntarily submit to something like that. The religion, for example, is the same kind of word, that which holds together the reliance on such a thing, like the timbers of a ship at sea to keep it from falling apart or something. The reliance of things, a religion, you know, that it's not dissimilar, and for some people it is well, abstractly via definition, you know, that this ontological commitment to a theory, that there exists one at all, is that there exists a true, consistent, complete, concrete one. So it must be something like that. And then, of course, as for the usual notions of man's religion, and that there's something bigger than us, and so that we're together, being on a boat of sorts, bound together by the same sort of overall thing. That's deism is considered super scientific, and that's part of what's called the voluntary submission to an ontological commitment, that something has to be true. I mean, part of being a thinking being is personal will and freedom of will, in a sense, and it's usually called the instinct for self-preservation or survival instinct. Then the idea of the human thing is this natural voluntary submission to an idea that's greater, to take it so that then that's along the lines of an informed kind of thing. That is an act of conscious free will in this manner. So these are some of the necessary desiderata requirements for the theory of everything to keep coming up from that. Because then, as that keeps going, all of a sudden mathematics and logic start being always true. Never false. How can that be? Well, we have our Comenius and Coleridge language. They just kind of start true and result even entertaining the proposition that there is a fallacy, and just leaving that as a prototype for a fallacy. And then anything else that is a fallacy can just be shown ex falso nihilum. That's what so arises from it as well. When a lie is discovered, that's a truth. But truth is discovered, lies are invented. When a lie is discovered, that's a truth. So then with the theory with truth in it, then we can take all our different discourses on theory as if the logical positivism today, reattach them to this teleological theory, not necessarily a teleological theory, but a teleological theory. This teleological theory, that at least is true, that there is one at all to attain to, that there is one at all to prefer a voluntary submission of an ontological commitment at all, because otherwise to each their own, and then that's nothing for anybody in the objective-subjective distinction. That then this theory has a lot going on with regards to how great it can be. And so that's as I got to studying where I wanted to go with this, and as I've been kind of dragging it out a bit, was it just kind of to establish that after learning about mathematics, then I wanted to be competent at it. Then when I learned how big it was, and that the formulas eventually were kind of like beyond what I could fit in my head, I said, well, I'll be back, because I need to learn a lot more to understand how these things are going to be before I get to them. And the mathematics. And then, studying for some years, and then coming back, it's like, no, now I have computers. I can basically program a computer. Now I can do anything with that. And well, that's pretty big too. You gotta learn everything if you're gonna know much. These kinds of worlds. And so now I got back around to it, and it's like, well, I got to figure out infinity and continuity, and it's like, all right. Now it's like, well, things are looking a little. At least I've got it in one box. I mean, I'm looking around. I mean, there's lots of detail in here, but it is kind of in one box here, kind of. And it took a while. It's like, what do you mean paradoxes? No, all these paradoxes had to be resolved somehow, which is an exercise in itself. But I from what I understand, there are no mathematical paradoxes left at all. There's mathematical truth at all, so which is nice. So keeping on with that, then like, well, what about all the theories of the physics and their fields? Like mostly quantum mechanics and relativity. After all, the classical of mechanics and kinetics and kinematics and heat and light and electricity and magnetism largely, and all this stuff to do with all these things, and chemistry, biology, this. It's like, yeah, those are pretty big fields. So I decided by then I'm still just keeping with the foundations. See, so you got to have at least one theory that's good for everything. So we have a lot of theories that are good for lots of things, but there is one with everything in it. So this is what you can look to arrive at then for each of these fields. Then figuring out what's true in them is fine. And then the idea being then is these other things come along that it can never have untangled a paradox or something like that. It always must be sort of a stopgap or a measure or a hedge. It always must be something affecting to reflect that when something's put down or put aside, it's not obviated. It's consciously this way, because it will return. It's its own nature for it to be a thing. So this is how much I've enjoyed this for some time. Let's see, here's some books. Modern Logic, this is Barnes & Noble. Exercise and Answers, Norman L. Thomas. Key to your textbook. Connectives. Connectives or connexives are regular notions that symbols are connected by connectives. So that's matters of relation. We have our terms, propositions, and predicates, and relations, and so that's it. Here's the book on medieval philosophy that we were looking at the other day. From Augustine, this is St. Augustine of Hippo, a Roman, an African, from like Tripoli or around this area of Hippo. And Augustine was a great Platonist. And so in our study of Plato and these ancient Greek philosophers, the Platonists are the school that there are these perfect, enduring ideals, and they already exist. So this is the same theory, of course. This perfect theory is still the same theory as it's ever been. So Augustine really, he wrote a bunch of great books in terms of that. He also wrote these books called The City of God, and he basically makes a moral distinction between good and evil, and makes it so that ever since then it kind of began the scholastic age in what became the Christian churches, and it was also very very influential in Islam and in throughout the world, in the sense that it established that it was good to be good and bad to be bad. So that's just something to consider. To Buridan. So Buridan is like, he's a philosopher, and again, this is ranging from like 500 to like 1200 or something like that. I mean, over a long period of time when not too much happened in terms of the development like we see today. Like between 1840 and 1850, there was more development scientifically and technologically than there was in these 700 years. But mentally, and as of the course of the progression of these ideas of just the thinking concepts throughout the world, that occurred as if in a day, when the Congress between these countries and these diverse parts of all over the world were not great. That it results, though, that these are the same club of thinkers whose names are known all kind of pretty much since then, everywhere. The universities, this was discussed. Buridan is probably most famous for the notions of several, again, mathematical thought experiments that become paradoxes and have to be thought out. They have to be resolved. So he says, well, you take a donkey and you put it between two bales of hay, but it's equidistant from both bales of hay. It cannot decide, so it will starve. And it's called Buridan's donkey. And the idea is that it will never make a decision because both of the prospects are equally good or bad. And so there's no inclination between the decision of a prospect to pick either one. Then the usual idea is well, he'll pick not starving, and then they're both just, either one is just whatever one he reaches first. And then that's the usual way to look at it. But another way to look at it is that there's a balance, is that it's indecidable. So that's just an example, one of the things that gets attached all throughout the rest of history to kind of a lot of these different kinds of mentions of, like, the branching problem or the Entscheidungs problem. Sometimes they call that Church-Rosser theorem or something like that. It's like, well, what could ever get figured out, or why would anything ever move randomly, or would it always return to the same spot? It varies. It varies a lot. So I guess that's about it for today. I don't really have too much else going, because probably this is just one giant waffle trying to figure out for the identity dimension, of course. There was mention the dimensional resonators and alternators, and that's something that's been missing because it's a very important concept for this moment in motion. And then Zeno's swath, the hypercube and the hypercube distance, that this is all just taking this infinitely many higher orders of acceleration and then saying that starts a domino effect, and the first one falls infinitely fast, and the last one falls 0. And so it adds up to 1. The hypercube distance equals 1 and is a straight line between 0 and 1. So these are the kinds of things. Photon propulsion. Source book of the space sciences. A mode of rocket propulsion different from any of those already considered, and possibly even more in the realm of speculation, is the photon rocket. It is of unusual interest because it offers a prospect of space travel speed approaching that of light. I just wanted to see if he makes any purely otherwise skeptical conclusion possible. The specific impulse is equal to the exhaust velocity divided by the acceleration due to gravity at Earth's surface. So he's expressing that because of the fact of the equivalence principle not holding up, except as about being terrestrial, that by the enormous amount of power required to operate the photon rocket, a thrust of 1 pound force would necessitate the expenditure assuming all the energy would be converted. That's so these days they have what's called the ion propulsion is generally considered not taking too much of the course of what's called the impulse, the response media or whatever, rest mass, rocket fuel. That anyways, this idea of here that there's, even since the 1980s, a photon rocket is just another example of something just outside the milieu and waiting to find an application from science instead of just using this embarrassment of computing to TikTok the biz kits each coffee break, you know, that these are the kinds of the ways that it's possible to imagine that a bunch of people coming up instead with mathematics as the study of sorts in this universal language could really arrive at a lot of different technological advancements, or that some could, in so few words. Well, I shall so hope you had a wonderful day and this week and such. And what to take away from this episode is this. Theory is individual. Everybody has their own working theory. A theory exists of a universal language called mathematics that embodies anything that's true. It's posited that anything so perfect as that it's only the domain of such a being could make it so. And then it's also it's posited that it exists for the fact that it can. It does. Yes, my sign. So the second part is that it's possible to develop one's own ontological commitment to a theory, and the idea is to kind of pick the best one. So besides the questions of life's moral questions and questions for one's own gain, and for survival and the instinct of self-preservation, and also for that of one's friends and family, pretty much, or gain and survival, then and nutrition and sustenance and propagation and all this kind of stuff, often called Maslow's needs. At the top of that little chart of the checklist of the laundry lists and such is self-realization, and what it involves is having a theory of what's true and being able to relay it to other people, that it's just something that so carries by itself. Now, today we have enough of a language of logic and mathematics to arrive at one with no paradoxes left in it. Not only is it explored that there are paradoxes from the foggy, vague areas, the gray areas, but after deconstructive accounts and putting them back together, it's possible to do so where there are no paradoxes left. It's true. It's consistent, constant, complete, and concrete. True. So then that's to be said that for figuring out what is theory of mathematics to follow is for the analog and discrete, and the digital and the analog, as it's usually framed in juxtaposition, the continuous and discrete, and that these laws of large numbers are where the analytical character will be so established to basically make for convergence and emergence. Those two concepts effectively defining that for the infinite limit and the continuum limit, that this is where then what could be built from that is for these for the models of physics, there's a flux in the superfluid and the supersymmetric and the supersymmetric again, and that's discussed here quite a bit in various brief and passing references throughout this concepts in the studies of path integral, the theory of relativity, according to Einstein and peers, and then the differential dynamics and this moment mechanics, that it can be so considered that there is a brief enough introduction to a theory with the science that there is one, and it should be pretty much standard, and it doesn't take a rocket scientist to have pretty much most of that conceptually full, then for that the particulars are their own business. That then it's possible to provide for it an ontological commitment, a voluntary investment, is a voluntary submission to that, with that being the most least untrue thing. Well, I suppose then this was mostly just ideological today. Well, have a great day. Goodbye.